Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last lecture, we studied aliasing and discretization errors in digital signal processing. In this lecture, we are going to study another error which may occur in digital signal processing, and that is related to what is called as windowing. So, a brief outline of the lecture is as follows. First, we will try to understand the term windowing, then we will try to see or analyze the effect of windowing of a continuous signal on the frequency domain representation of the signal. We will take example of a cosine signal to analyze the effect on the frequency domain representation. In the process, we will also try to look at what is leakage error, and then we will look at effect of windowing of a discrete signal on its frequency domain representation, which is nothing but DFT of the signal. Then at the end we will try to look at what are window functions or windows and how they help to reduce the leakage error. So, today's topic is windowing. So, let us try to understand first what is windowing. So, when we want to measure vibration signal, then we have to start the process of measurement at some point and then stop the process at some point, right. And let us say if the vibration signal is a transient signal or finite length signal, okay, then in that case we can start the process just before the transient signal starts, and then we can stop the measurement process when the transient signal has elapsed, okay, it has died down completely. So, in this way we have the option of measuring the complete length of a transient or finite length signal. But in many situations the vibration signal occurs or continues for an indefinite length of time. For example, the vibration experienced by passengers sitting in a car which is moving, the vibration occurs continuously as long as the car moves, okay. So, the vibration signal continues indefinitely. So, in this case then we will have to measure a finite length of signal, okay. So, we will start the measurement at some point and stop, and then in the process we will measure a finite length of signal. Now, measuring the finite length of signal can be looked upon as multiplication of the signal which is continuing indefinitely by a function or window function, okay, and that is basically referred as windowing of the signal. So, let us try to sketch the signal. Let us say we have the signal XC. C refers to the continuous nature of the signal, and let us say the signal is like this. Let us say it is a continuous signal and varying in this manner. And now process of starting and the stopping of the measurement can be looked upon as multiplying this signal by a function which is unity over the length over which we take the measurement and 0 elsewhere outside that duration, okay. So, we can sketch that signal as, let us call that as signal W as a function of time, and the signal is having unity value over the length t by 2 and minus t by 2. So, therefore, if we are measuring the length t of the signal, then the signal is having unity magnitude over this duration t and then 0 elsewhere. So, when we multiply xc with w, then we end up with a signal which can be shown like this. So, here we can call this as the windowed signal xw, okay, and then we have this record length like this. Something like this. So, this is the length minus t by 2 to t by 2. So, this is the windowed signal, and this process can be mathematically represented as x c t. If we multiply this by signal w t, right, then that gives us the windowed signal x w t, right. So, it means that the windowed signal x w t is nothing but the product of the continuous signal x c t and the window function w t. Okay. So, this w t is basically called or referred as a window function or window. I can call this as the window function or just window. Okay. And this equation effectively represents the process of windowing, right. So, this equation represents windowing of the signal x c t, correct. Therefore, window is nothing but equivalent to a mathematical process of multiplying the continuous signal by window function. And in this case, this function is like a rectangular pulse, and hence this window function is referred as rectangular window. This function is basically a rectangular window function. So, I can write here this is a rectangular window. Okay. Now, the question is that if that is so, that the window signal xwt is equal to product of xct and wt, and then we would be interested to know that if we now find the frequency domain representation or Fourier spectrum of xwt, then would it be same as the Fourier spectrum of the original signal xct, or would it be different, and if it is different, in what way it would be different. So, therefore, now we are going to talk about that what is the effect of windowing of a continuous signal on the frequency domain representation of the signal. Okay. Let us go to next page. Effect of windowing of a continuous signal on the frequency domain representation of the windowed signal, right. Okay. Let us try to look at this. To analyze the effect of windowing on the frequency domain representation, we take the Fourier transform of the windowed signal, right. So, taking Fourier transform, okay, then what we get. So, if you take the Fourier transform of xwt, we get the Fourier spectrum of xwt, and let us represent it by capital letter X, okay, xw omega. And then on the right hand side we have two time domain signals being multiplied, and as we mentioned earlier also that multiplication in the time domain corresponds to convolution of the corresponding spectrums in the frequency domain, and therefore on the right hand side we will have 1 upon 2 pi, then we have first the Fourier spectrum of the continuous signal, that is x c omega, okay, capital X c omega, and then convolution of this with the Fourier spectrum of the window function, that is w omega, and then we can write this as x w omega is equal to 1 upon 2 pi, and then integration from minus infinity to plus infinity, right, w g. So, g is a dummy frequency variable, right, multiplied by x c omega minus g into dg, right. So, that is nothing but the definition of the convolution. So, now in order to work out x w omega, we need to first of all find out what is the Fourier spectrum of the continuous signal and what is the Fourier spectrum of the rectangular window function. So, let us work out these transforms first, and then we will substitute back those transform equations into this convolution equation to obtain the Fourier spectrum of the windowed signal. So, let us work out what is the Fourier transform of x c t. Now, for the purpose of discussion here, let us take the example of a cosine signal. Okay. So, let us say if I have a cosine signal which is given by say a cos omega 1 t. So, the frequency of the signal is omega 1, and let us take this signal. Let us write this signal first of all as x c t using Euler's identity. We can write this as a e to the power I omega 1 t plus e to the power minus I omega 1 t upon 2, right. And now we take the Fourier transform. So, if you take the Fourier transform, x c t can be written as x c omega, okay. And then we know that the Fourier transform of e to the power I omega 1 t, it is 2 pi delta function omega minus omega 1. So, that Fourier transform of e to the power I omega t is 2 pi delta omega minus omega 1, right. And similarly, the Fourier transform of e to the power minus I omega 1 t is 2 pi delta omega plus omega 1. So, we have 2 pi delta direct delta function omega plus omega 1, okay. And then if you simplify, what we get? We get a pi, right, delta omega minus omega 1 plus a pi delta omega plus omega 1, okay. So, this is nothing but the Fourier transform of the continuous signal a cos omega 1 t, which is the cosine signal with amplitude a and frequency omega 1. Let us now work out the Fourier transform of the window function. Let us go to next page. So, now we are going to look at Fourier transform of time signal Wt, okay. So, let us invoke the definition of Fourier transform. So, we know that the Fourier transform of Wt would be W omega, and this would be equal to integration of Wt into e to the power minus I omega t into dt with t varying from minus infinity to plus infinity, right. So, now we note that the window function is unity over the magnitude minus t by 2 to over the duration minus t by 2 to plus t by 2 and 0 elsewhere, and therefore, the limits of integration here we can change to integration minus t by 2 to plus t by 2, and then W of t is nothing but unity, right, into e to the power minus I omega t dt, correct. And therefore, the integration of e to the power I omega minus I omega t is e to the power minus I omega t divided by minus I omega, and then we have to apply the limits from minus t by 2 to plus t by 2, correct. And now, if I apply the limits, then I get e to the power minus I omega t by 2, right, minus e to the power I omega t by 2. So, if I use Euler's identity here, then I get 1 upon I omega, and then in the bracket I have e to the power I omega t by 2 minus e to the power minus I omega t by 2, which is nothing but 2 I into sine omega t by 2, right, that is what we get. And this becomes, if I cancel I and I, then if I multiply by t and divide by t, then I get sine omega t by 2 divided by omega t by 2. So, this is nothing but the Fourier transform of the window function, that is W omega. And this function, actually if you see this function, it is in the form of a sin c function. Okay. So, we know that the sin c function is is referred as to an expression which is in the form of sin theta by theta, correct. So, that is called a sin c function. So, we can see here that theta is nothing but omega t by 2. So, therefore, this spectrum of the window is in the form of a sin c function. And so, let us now try to sketch these spectrums. Okay. So, let us do it for the continuous signal as well as for the Fourier spectrum. Let us go to next page. So, for the continuous signal, the the spectrum would be, if I sketch here say x c omega like this, then the spectrum we saw the expression was a pi delta omega minus omega 1 and plus a pi delta omega plus omega 1. So, therefore, the spectrum of the cosine signal, it consists of two impulse functions, okay, located at minus omega 1 and plus omega 1. So, therefore, we have this impulse at omega 1 and then we have another impulse at minus omega 1. Okay. And the strength of this impulse, each of these two impulses, strength is a pi. So, this is nothing but a Fourier spectrum of the cosine signal. Let us also now sketch the Fourier spectrum of the window function, and that spectrum looks something like this. We see that this spectrum is having a main lobe like this at the center, okay, and then we have the side lobes like this. So, here we are showing the magnitude of the WG, W omega, and on the negative frequency also it is there and it is symmetric like this. Okay. And then we see that this spectrum, it intersects the omega axis, right, which means the magnitude of the spectrum becomes 0 at those frequencies. And what are those frequencies? So, we know that the spectrum, the equation for, let me write down that again here, that is W omega is equal to T sin omega t by 2 divided by omega t by 2. So, we see that W omega is 0, right, at frequencies at which omega t by 2 is integer multiple of the pi, right. So, therefore, here n can take values from plus minus 1, plus minus 2, plus minus 3 and so on. So, at these values W omega would be 0, and that is why we see that at those frequencies the Fourier spectrum of window function intersects the its amplitude is 0, and we can therefore find these frequencies as n 2 pi by t, right. And if t is the length of the window function, and if we call that as the fundamental frequency, then we can call this as n omega naught, okay, where omega naught is the value 2 pi by t, where t is the length of the window function or the length of the time record. So, therefore, we can mark these frequencies here. So, this frequency is nothing but omega naught, this frequency is 2 omega naught, this frequency is 3 omega naught and so on. Similarly, on the negative axis we have minus omega naught, minus 2 omega naught, minus 3 omega naught and so on, right. And of course, this value at frequency 0, the magnitude of the window function is t, right, which is also same as 2 pi upon omega naught. So, in this way these figures basically give us the on the left hand side we have the Fourier transform or Fourier spectrum of the cosine signal, and on the right hand side we see the Fourier spectrum magnitude of the window signal. Let us now determine the Fourier spectrum of the window signal. Let us go to next page. Let us now substitute the spectrums we got in the equation for convolution, right? And let us write that equation again. So, we had x w omega, this was equal to 1 upon 2 pi integration w g, right, into x c omega minus g into dg, with g varying from minus infinity to plus infinity. Okay. So, now we substitute Wg here. So, Wg, which is the spectrum of the window function, that spectrum we got as t, then we had sine omega t by 2. So, in place of omega now we will write g, because g is the frequency variable here. So, we will write g t upon 2 upon g t upon 2, right. And then in place of x c omega minus g, we have the spectrum a pi delta, right. We had omega minus omega 1, right. So, in place of omega we have omega minus g. So, we have omega minus omega 1 minus g, right, plus a pi omega plus omega 1 minus g, okay, into dg. Okay. Now, how we evaluate this integral? So, we are going to make use of the shifting property of the delta function, and in this case the delta function will pick the value of the function sin gt by 2 upon gt by 2 at g is equal to omega minus omega 1 and g is equal to omega plus omega 1, and therefore, we can write this as 1 upon 2 pi t sin omega minus omega 1 t by 2 divided by omega minus omega 1 t by 2, right. And then it will also have another term sin omega plus omega 1 t by 2 divided by omega plus omega 1 t by 2, right. So, if we simplify this, what we get? So, we get I think, yeah, a is also there, which I have missed here. So, I have a pi as well. So, let me write that a pi here, okay. So, then this pi cancels out, and then I have got result that a t by 2, right, into bracket sin omega minus omega 1 t by 2 divided by omega minus omega 1 t by 2 plus sin omega plus omega 1 t by 2 divided by omega plus omega 1 t by 2, okay. So, this is nothing but the spectrum of the windowed signal. And what we observe from here? So, we observe that now we have that spectrum of window function that is now getting replicated at the frequency omega 1 and minus omega 1, okay. This we can see the first term here on the right hand side is sin omega minus omega 1 t by 2 divided by omega minus omega 1 t by 2. So, this is nothing but a sin c function, right, or the window spectrum located at omega 0 to omega 1. And similarly, the second term, which is sin omega plus omega 1 t by 2 upon omega plus omega divided by omega plus omega 1 t by 2, that again represents a sin c function or the window spectrum located at omega 0 to omega 1. So, therefore, the convolution of the spectrum of the window function with the spectrum of the cosine signal, it has led to the appearance of the copies of the window spectrum at the frequency of the cosine signal, right. So, let us try to sketch this on the next page. So, let us sketch the Fourier spectrum of windowed signal. Okay. So, basically we are going to sketch the magnitude of the x w omega. So, like this. So, this is nothing but magnitude of x w omega. So, therefore, now we will have the spectrum of window function appearing at omega is equal to omega 1. So, this is omega 1, and then we have these side lobes also here as they were in the spectrum of the window signal, like this on both sides. Like this, and then this also appears at frequency minus omega 1. And then we have side lobes like this. Okay. So, therefore, this is nothing but the frequency domain representation of the windowed signal. And what are the observations? We see that this spectrum is not same as exactly same as the spectrum of the continuous signal. So, if we sketch for comparison and for a quick reference the spectrum of the original signal which we wanted to analyze, and let us sketch that here, which is nothing but x c omega, then that basically had two impulses here like this at omega 1 and another impulse at minus omega 1. So, this is the we can say the true spectrum or spectrum of the signal, original signal, and this is nothing but the spectrum we obtained. The spectrum we obtained from the measured or windowed signal, because it is the measured signal is nothing but the windowed signal, and we see that they are not same, they are not identical. So, let us also sketch the Fourier spectrum of the window function here for comparison. Let us sketch that here. So, this is nothing but the spectrum of the window function. Wg omega is a function of omega. So, this W omega has a main lobe. So, this is the main lobe, and then these are the side lobes. So, all these are the side lobes. These are also the side lobes. So, if we look at the spectrum of the window signal, then we can explain why the spectrum of the window signal looks the way it is appearing, right. So, we see that the main lobe of the window spectrum, it basically causes appearance of a main lobe at the frequencies which are present in the true signal, right, which are present in the actual signal. And then the side lobes, they give rise to appearance of additional frequencies in the neighborhood of the true frequency components. So, in this case omega 1 is the true frequency component, and then we see appearance of side lobes in the neighborhood of these frequencies in the spectrum of the windowed signal. And these additional frequency components, right, they are not present in the true spectrum, okay, and therefore, these are nothing but spurious frequency components appearing in the spectrum of the windowed signal. So, in a way we can say that the signal energy has leaked from the main frequency component, right, to the the components in the neighborhood of the true frequency component, right. Some energy has leaked, and this is therefore named as leakage error. Okay. So, this appearance of additional frequency component. So, these are the additional frequency components. Okay. They are basically referred as leakage error. So, this is also leakage error, this is also leakage error. So, all these are basically referred as the leakage error. So therefore, leakage error is the basically the error which is occurring due to windowing, okay. And the leakage error is because of the side lobes, and the main lobe, it basically causes the broadening of the true frequency component. The frequency component in the true spectrum is basically in the form of impulse, but in the spectrum of the windowed signal, the frequency component at omega 1 has got broadened because of the main lobe, right. So this is referred as smearing. So this broadening of the peak, right, or the true frequency, right, is referred as smearing effect. Smearing effect. So main lobe causes smearing and the side lobes give rise to leakage error. So now we are going to study effect of windowing of a discrete signal on its frequency domain representation. So now we are going to study effect of windowing of a discrete signal on its frequency domain representation. Okay. So in practice, we measure a discrete signal, and therefore we can look upon the process of windowing of a discrete signal as the product of the discrete signal and a discrete window function, and therefore we can write xwn, which is the measured windowed discrete signal, as a product of xn multiplied by discrete window, right. So this is discrete windowed signal, right, and this is discrete window. Now to study effect of windowing of a discrete signal on its frequency domain representation, we will take its Fourier transform, and the signals here are discrete, and therefore when we take Fourier transform, they are nothing but discrete time Fourier transform, right. So when we take Fourier transform, taking Fourier transform, right. So what we will get is a discrete time Fourier transform. We will get discrete time Fourier transform, which is DTFT. So it means here we will take the DTFT of XWN, XN and WN. We will have to take DTFT of this signal. And we have studied earlier that DTFT is nothing but a periodic spectrum, okay, and in which one period of DTFT corresponds to the spectrum of the corresponding continuous signal, okay, and in practice we basically take DFT of the signal. And what is DFT? DFT is nothing but the sampled version of one period of DTFT. So this we have studied in earlier lecture. So in practice we take DFT, right, of the signal, right. And what is DFT? DFT is sampled version of one period of DTFT, correct. So it means we draw samples of DTFT, and the samples we draw, they depend on the frequency spacing of those samples, and the frequency spacing depends on the length of the time record. So if T is the length of the XWN, right, then the samples in the DFT would be in the DFT would be at minus n by 2 omega naught going up to minus omega naught, then 0, then plus omega naught, then plus 2 omega naught, going up to n by 2 minus 1 into omega, right. So, if we have n number of samples, the length of the the signal is t, and if the number of samples are n, okay, then the frequency lines or the samples in the DFT would correspond to these frequencies, and here of course the omega naught is nothing but 2 pi upon t, correct. So, therefore, the DFT corresponds to the samples of DTFT at these frequencies. Now, to understand that how windowing of the signal affects the discrete Fourier transform, and whether the discrete Fourier transform we obtain does it match with the discrete Fourier transform of the signal xn, which is the original signal. Let us take an example to understand the effect of windowing on a discrete signal. So, here we are taking the example of a cosine signal. So, the true signal is xct is equal to a cos omega 1 t, right, and let us say we have measured one period of the signal, the time length or the record length is equal to one period of the signal. So, therefore, let us say that t is equal to 1 period, right, or t represents 1 period of the signal, right, and let us say we have recorded n number of samples, okay, and with this now we determine the DFT of the signal. So, it is seen that the DFT of the signal comes out to be like this. So, let me show here the magnitude of DFT, right, and here omega, and the frequency lines in the DFT would be at frequency omega naught, 2 omega naught, 3 omega naught, and so on, right, and in this, and on the negative side we will have minus omega naught, minus 2 omega naught, minus 3 omega naught, right. So, we will have the lowest frequency on the negative side will be minus n by 2 into omega naught, and the highest frequency on the positive side of the DFT would be n by 2 minus 1 into omega naught. And then we see that the DFT basically reveals a component at omega naught and at minus omega naught, and at other frequencies the amplitude is 0. Okay, and then in this case this omega naught turns out to be actually equal to omega 1, right. We see that this frequency of the first line is actually the frequency of the original signal, and in this way the DFT we have got is the accurate representation, is the correct representation of the frequency spectrum of the original signal, because the frequency frequency spectrum of the original signal should contain frequency component only at omega 1, and the DFT also contains provides the same information, right. So, we see that this is correct representation of the DFT of the original signal. So, now the question arises that in this case the windowing has not introduced the leakage error or smearing of the frequency components. So, why it is so? Why the windowing has not affected the DFT, right. So, to get insight, let us look into the DTFT of the signal and see that at what frequencies the DFT draws samples from the DTFT. So, let us sketch the DTFT. So, this is omega, okay, and the frequency of the main lobe of DTFT is at omega 1, okay, and this lobe main lobe looks like this here, and then we have side lobes like this, okay. On this side also we have the side lobes, right, and then we also have the main lobe and side lobe on the located at minus omega 1, and so this main lobe would be here, and then we have the side lobes. like this. Let us now also overlay on this the frequency lines in the DFT. Okay, so let me first write down that this is DTFT, right, of x CN, right, or XN, we can just call it XN, that is the discrete signal. And now let us overlay on this the DFT lines. Now the DFT lines would be at one line would be at the 0 frequency like this, right. Next line would be at omega naught, right, and omega naught is nothing but 2 pi by t, because t is the record length. Okay, and since t also is one period of the signal, omega 1 which is equal to 2 pi upon the period, right, and since the period is also the record length t, so we see from here that omega naught is basically equal to omega 1 in this case, and that is why we have the DFT sample being drawn at omega 1, right, and then the next sample being drawn is at frequency 2 omega naught, and this 2 omega naught is actually here, right. So, and then the 3 omega naught is this one, and 4 omega naught is this one, right. Similarly, on the other side we have the sample being drawn at the main lobe like this, okay, and then we have the frequencies discrete lines located in this manner. Okay. So, also we should note that the frequencies at which DTFT is 0 is those frequencies are 2 omega 1, 3 omega 1 and so on, right, and the DFT lines, they are at frequency, this is omega naught, 2 omega naught, 3 omega naught, 4 omega naught and so on. So, what is the observation? The observation is that the DFT lines, the first line in the DFT is located at the true frequency of the signal, okay, and the other frequency lines, they are located where the DTFT magnitude is 0, and that is why we see that in the DFT we see a peak amplitude at frequency omega 1, while 0 amplitude at other lines of the DTFT. Okay. So, it means that the DFT draws the sample in the DTFT where the true frequency exists and where the amplitude is 0, and that is why the DFT is not affected by leakage error or smearing effect. Okay. Can we explain this result also using some physical justification? Let us go to next page. So, let us try to understand that why the DFT in this particular case, where we have recorded one period of the signal, turns out to be the correct representation of the frequency content of the signal. Okay. So, we note that in this case the signal we have recorded is like this. We have the one period of the signal being recorded. So, let us sketch that one period of the cosine signal like this. So, these are the samples which are being drawn like this. Okay. So, this is one period of the signal. So, this is one period, and t is nothing but one period of the signal. And when we find DFT, we essentially find the spectrum of a hypothetical periodic signal obtained by repeating this length t periodically, right. So, the hypothetical signal which we are analyzing can be sketched in this manner, so that because this signal is now repeated like this. So, this is the repetition, and therefore, on this side also we can see that the signal is being repeated like this. Okay. So, this is basically the hypothetical periodic signal obtained by repeating the record T, right. The record T, if we repeat, then the signal we get we refer as the hypothetical periodic signal, and when we find DFT, we are essentially finding the discrete Fourier series of this hypothetical periodic signal, right. And what we note that this signal which is periodic signal exactly matches with the original cosine signal, right. And that is why the spectrum we get from this hypothetical periodic signal happens to be the true or the correct representation of the spectrum of the original signal. Okay. So, this clearly explains that why in this case the windowing has not affected or introduced leakage error or smearing effect in the DFT. Let us take another example. Let us go to next page. Let us take another example, right. So, in this example, now we are going to take the same signal as we took earlier, which is XCT A cos omega 1 t, but now the record length we are taking is 1.5 times the period of the signal, right. So, if t is the time period of the signal, which is actually equal to 2 pi upon omega 1, right. Then let us say we have recorded a length equal to 1.5 t, right, and let us keep the same sampling frequency, right, and then let us say that we obtain DFT of this signal, and the DFT that would result would look something like this. So, here we are showing the magnitude of DFT, and here we have omega, right, and then we see that now the frequency lines in the DFT again would be equal, so let me also write here that the frequency lines in the DFT that would be dependent on the fundamental frequency, right. So, if omega naught is the fundamental frequency, the frequency lines would be minus n by 2 omega naught, minus omega naught, 0 omega naught, going up to n by 2 minus 1 omega naught, and here omega naught is actually equal to 2 pi upon 1.52, that is the fundamental frequency. So, therefore, the different frequency lines here would be this is omega, then we have omega 2 omega naught, 3 omega naught, and then we have minus omega naught, minus 2 omega naught, minus 3 omega naught. So, this is omega naught, this is 2 omega naught, and this is minus omega naught, this is minus 2 omega naught. So, what we see is that the spectrum we get is something like this. It is symmetric like this, and like this. So, this is what we get, and if you mark the frequency omega 1 here, which is the true frequency of the signal, then it turns out that this is the true frequency is somewhere here, omega 1. Okay. So, what is the outcome? The outcome is that the frequency lines in the frequency components we get from the DTFT, they do not reveal the correct frequency spectrum of the original signal, right. So, we have a line at omega naught, we have a component, significant component at omega naught, and then another component, significant component at 2 omega naught, but there is no component at omega 1, which is the true frequency of the signal. And in addition, there are many other components which are having non-zero amplitude, and those are all spurious components. So, therefore, here we see that this is nothing but the leakage, right. This is the leakage error. Okay. This is all these frequency components, they do not exist in the true spectrum. So, these components do not exist in the true spectrum and represent basically the leakage error occurring due to windowing. And the components at omega naught and 2 omega naught, they are again the effect of the main lobe, right. The true component at omega 1 does not appear in DFT, but two components at omega naught and 2 omega naught appear, trying to represent the component at omega 1. So now why in this case the leakage error and smearing effect is seen in the DTFT. Again to get inside, let us sketch the DTFT. So let us sketch the DTFT and see that at what frequencies the DFT draws sample from it. So here again now the DTFT and the main lobe of the DTFT would be there at frequency omega 1. So we have this DTFT here like this. And also at minus omega 1. Okay. And now let us overlay on this the frequency lines in the DFT. So the frequency lines in the DFT, one frequency line is at 0 frequency, and then we have omega naught, then 2 omega naught, then 3 omega naught, 4 omega naught, right, 5 omega naught. So this is at omega naught, 2 omega naught, 3 omega naught, 4 omega naught. And similarly on this side we have this is omega naught, minus omega naught, then we have minus 2 omega naught, and then we have minus 3 omega naught, minus 4 omega naught, and so on. So now if you look at the frequency lines of the DFT and compare it with the DTFT, what we note is that now no longer the sample is drawn at the true frequency of the signal, which is omega 1, right, and also the samples drawn at other frequencies, they happen to be more close to the peaks of the side lobes, right, and which basically gives rise to the the leakage error or the spurious frequency components in the DFT, right. So in fact these are the components we are getting in the DFT, right. So and therefore this clearly explains that why leakage error is seen in the DFT. Let us also try to physically see that why the leakage error in this case is seen in the DFT when the record length is 1.5 t. So let us try to sketch the record we have captured. So we consist of 1.5 t, so it means one cycle of the signal and then half cycle of the signal more. So this is the signal we have recorded. So when we find DFT, basically we assume that this record is repeated, and then we find the DFT or DFS of the hypothetical periodic signal we get. So let us sketch that. So now when this record is repeated, the record basically the next record when it is repeated, it will be something like this. Correct. And similarly on this side we will have the record starting from it will go like this. So this is basically 1.5 t, where t is the time period of the signal, which is okay, and therefore when we repeat this, what we see that the hypothetical periodic signal we get, it does not match with the true signal. Okay, so this is the hypothetical periodic signal. Okay, hypothetical periodic signal obtained by repeating the record length 1.5 t. So this signal does not match with the true signal, and that is why we see that the spectrum we obtain is not same as the true spectrum, right, a spectrum of the true signal, and this is because of this discontinuity. So if you see here, the signal is discontinuous here, there is a discontinuity here. And this discontinuity basically gives rise to the leakage effect, right, leakage error. So therefore, from here we can conclude that if we can capture one time period or integer number of time periods of the signal, right, of a periodic signal, then the DFT obtained will be a true representation, will be a correct representation of the frequency spectrum of the actual signal, right. But if we are not able to capture the integer number of time periods, then the DFT of the periodic signal will contain leakage error. Okay. So we can say that if integer number of periods of the signal are measured, right, then DFT would be free of any leakage errors, right. There will be no leakage errors in the DFT. Let us go to the next page. Now we are going to talk about what are called as windows or window function. Window functions or simply windows. So in practice, often if the signal is periodic, we may not know the period of the signal, okay, and therefore it may not be always possible to record integer number of time periods. So in such a case, we will measure a finite length of the signal, which may not be equal to integer number of time periods, and in that case the leakage will occur, isn't it? And even if we have a transient signal, and if we are not able to measure the full length of the signal, and we are able to measure only the partial length of the signal, then also the leakage would occur in the DFT of the signal, right. And if the signal is continuing indefinitely and is random, then whatever record length we measure, the DFT of that would lead to leakage error. So then how is it possible to reduce this leakage error? So the need to reduce the leakage error has led to development of some functions called as window functions. Okay. So a window function is basically a mathematical function in the time domain. So a window function is basically a function is a mathematical function in the time domain. Okay. And this function therefore should be multiplied to the discrete signal. So when we measure the signal, right, and the discrete signal we have got, now we multiply this measured discrete signal by this window function, right. So there are different window functions available. And some of them are, say, Hamming, Bartlett, okay. These are some of the functions. Now to understand the effect of these window functions and how do they help to reduce the leakage error, let us try to compare the let us look at Hamming window function in more detail and compare the characteristics of this window function with the rectangular window. So let us look at Hamming window. Okay. So Hamming window is basically given by W of t is equal to 0.5 plus 0.5 cos 2 pi t by t, where absolute value of t is less than or equal to t by 2, right, where t is the length of the signal which we want to record, and this is equal to 0 otherwise. Okay. Therefore, if we sketch this window function, it may look something like this. Okay, this is Henning window function. Okay. So therefore, if we have signal x of n that we have measured, then we multiply this x of n by this window in the discrete after discretization Wn, and then we get the windowed signal, right, and then we find the DFT of the xwn, correct. So before we process the signal, we multiply the measured discrete signal by the window function and then do the processing of the signal. Let us go to next page. So to compare the effect of this window function, let us compare the Fourier spectrum of the Henning window with that of the rectangular window. So let us overlay the, so here we are going to plot the Fourier spectrum magnitude in dB of the windows functions, right. So the let us first of all plot the Fourier spectrum of the rectangular window function, and that function may look like this. Okay, and it is symmetric on this side. Something like this. So this is nothing but the Fourier spectrum magnitude of rectangular window, right. Let us now overlay on this the Fourier spectrum magnitude of the Henning window, and that may look something like this. Okay, so this is just a qualitative comparison. Like this. Okay, so this is Fourier spectrum magnitude of Henning window. Okay, and so what are the observations? If you compare the two, what are the observations? The first observation is that the height of the or amplitude of the side lobes in the Henning window, okay, is much smaller than the amplitude of the side lobes of the rectangular window. So amplitude of side lobes of, let me just write Henning window as HW, okay, of HW are smaller than those in rectangular window RW, right. The rate of decrease of the amplitude is more than the rate of decrease of the amplitude of the side lobe in the rectangular window, okay. The rate of decrease of side lobe amplitudes is more in Henning window than in rectangular window, correct. So because the side lobes are responsible for causing leakage, we see that if we use a Henning window, the leakage error will be smaller, okay. So due to this, leakage error is smaller with Henning window. And that is why if we want to use, we want to reduce leakage, we can use a function like Henning window and some other, and similar other windows also help to reduce the leakage error. The other observation is that the width of the main lobe in Henning window is more, right, than in rectangular window, correct. And because main lobe basically causes broadening of the frequency peaks, correct, smearing of the frequencies. So therefore, the ability to distinguish closely spaced frequency components is less with Henning window. Okay. So this smearing effect, what does it do? It broadens the frequency peaks, and if there are some closely located frequency components, then the distinguishing those frequency components becomes difficult because of the smearing effect. And because the width of the main lobe in Henning window is more, the ability becomes even lesser as compared to the rectangular window. Therefore, we say that the smearing effect is more in Henning window than in rectangular window, correct. So in practice, if these artificial window functions, if they are not used, then it amounts to using basically a rectangular window. No window functions, being used amounts to using a rectangular window. Okay. So just the process of starting and stopping the measurement amounts to applying a rectangular window. Okay. And if no function like Hemming or other window function is used, then essentially we are using a rectangular window. Okay. So in this way today, we looked at what is windowing, how windowing causes leakage error, and how leakage error can be reduced by using window functions. We can stop here. Thank you.